There is at least one person waiting. Let us probably wait for some time more. Anyway, start admitting.
Yes, sir.
Yeah, I am starting the YouTube live stream.
Yeah, and admit also.
Currently, it's showing that there are the two people who are waiting to get in. Yeah.
Yeah, no, we are taking care of that. Don't worry.
Okay, sir. Okay, sir.
Yeah.
So total participants, I think, are about 7 or so.
Yeah, slowly they come.
Yes, sir.
Okay. Yeah. About a minute more at least before we.
Yes, sir. Sure. Number of people I think joined are 10, 11.
Yeah,
I think so. 11 or so are joined.
I think at least 20% join.
Okay.
So we had around 300 registrations, I think.
Okay.
Yeah.
So I hope around 30 should join.
300. Yeah. Yes, sir.
You see, when it is no charge is there, then everybody registers.
Yeah.
But at
So
least those
yes.
who are interested will come at least.
Machine learning, I think gathers more some interest also.
Yeah, it's a hot topic these days.
Yeah.
Sure.
Presently, I'm seeing that about 13, 14 people. Yeah.
Yeah, not bad. Yeah. Yeah. Yeah, I think probably it's.
Yes, sir. We can start, I guess.
We can start. So let me welcome all the participants in this meeting of Math Clinic. So today's meeting is on one of the hot topics nowadays, what is called machine learning. So we thought it's a good idea to have a basic overview of machine learning. And we were happy that Professor Niteesh had agreed to deliver a talk. Professor Niteesh is in the Department of Mathematics at Shiv Nadar University. He obtained his PhD from the University of Delhi in harmonic analysis. At Shiv Nadar University, he has expanded his research interests into machine learning, artificial intelligence, topological data analysis, and dynamical systems. He has more than 10 years of teaching experience and has developed many courses, including data learning, which are taught normally to computer science students as well. His recent work mainly focuses on applications relevant to industry and society. So with this brief introduction, let me welcome Niteesh for this lecture on math clinic. So I will request him to start the topic. Please, Niteesh.
Yes, sir. Thank you, sir. And I will keep this lecture at a very basic level, and the main idea behind this this talk is to give a reasonable overview of ML to maths maths students. So basically our talk begins by looking at the two very popular scenarios which one encounters in ML. So scenario number one will be some data which is of this shape. So basically, if you look at the standard nomenclature of this existing data file, information in your provided data file is given as column number 1, 2, 3, and 4. Okay, there's a subtle difference which comes between the various columns. We are designating the last column as y. Okay, so this current example that I am projecting on the screen is a consequence of one project which we did for a bank. Okay, so the historical records of the various customers in that bank are basically n. Okay, and the data which the bank has collected corresponding to every single customer is gender, balance loan, and on the basis of these three parameters, the bank has tabulated its decision in this column y. So whatever values that you are seeing in the last column, in the credit approval column, is going to be either yes or no. That is precisely what the manual decision was taken by the bank for client number 1, client number 2, so on and so forth up till client n. Okay, and now if you look at the very first row, the numbers corresponding to your client number 1, just for the sake of simplicity, we are writing down and as x11, x12, all the way up till x1, 1 to the 1, 3. So there were certain designated numbers there, and as far as that original data went, genders was either a male or a female, which we then coded from our side as males were designated by 0 and the females were being designated by 1. So for all mathematical purposes, the xij's are numbers. Okay, but the main thing is that this credit approval to the thing, it cannot be any number. It needs to be either yes or no. We are free to code up yeses as 1 and no's as minus -1. And we also looked at a problem which was little bit similar to this data. Okay, so the corresponding problem that we also worked on, that the data set had a template which was pretty similar the one before. The only fundamental difference between template number 1 and template number 2 is the kind of values which are being taken by your response response y. So in case we find that the response variable y, the values taken by that are discrete, we shall label that underlying scenario as a problem of classification. And if we find that the response could be any number under the sky, that means that it takes up any continuous value, we label that underlying scenario as a regression one. So with reference to our template number 1. Sorry. So with respect to our template 1, where we are assuming that our response variable takes on discrete values, either yes or no. And for mathematical convenience, we shall designate no's by -1, and we shall designate yeses by plus 1. So our purpose here, as far as building that machine learning model goes, our purpose here is to come as close as possible to the actual functional relationship between your variables x and your corresponding response y. And what our main objective is, that whatever model or whatever relationship that we manufacture between x and y, that relationship should be such that when we apply that function to two sample points which are brand new, sample points which is completely not present in what our starting data set was, if we apply that function to those unseen points, the accuracy with which it gives out labels yes or no, that accuracy should be high. Okay, so that means we are looking for that relationship which performs well on data which is not seen. Okay, and now to make the entire framework precise, let us represent our data set number 1 in a more convenient form. So if you look at the very first row, the numbers over there are x11, x12, and x13. So let us, for convenience, call this entire tuple x11, x12, x13 as x1. So your observation number 1 is now x1. Similarly, the tuple in the next row, leaving aside the corresponding y's, you would call as x2, and then x3, so on, so forth, up till xn. So this entire data frame can now be neatly formulated like this. So as pairs, x1 comma y1, next point it is x2 comma y2, and so on, so forth, because there are capital N number of sample points. So the last one is x1 xn comma yn. The values of your response corresponding to every single xi is being designated as yi. Okay. Okay, and now if we are at the moment concentrating only on our template number 1, where my yi's are either yes or no, and in my mind I am keeping no's as -1 and I am keeping yeses as +1. Okay, so every single yi over here is going to be either a -1 or a +1. We are searching for a model that accurately predicts the labels for the clients not yet encountered by the bank. Okay. Now the thing is that if I take you for a moment back, our goal was to look for a functional relationship, or we want to basically come as close as possible to what the exact functional relationship was. So that makes me make one fundamental assumption, and this assumption is going to be central to the overall mathematical framework of ML. That assumption is that there exists some functional relationship between X and Y. Okay, now these observations X1, X2, all the way up till Xn, we treat them as one particular sample. That means we are assuming that these are drawn from some larger population X. So if we call the entire population space as capital X, then the domain of your function f, which you are searching for, becomes this X. And the purpose of your function is to predict labels corresponding to every single observation inside capital X. So that means it's a mapping into -1, 1. So corresponding to every single X belonging to capital X, your fx would be either yes or no. Okay, and which means that in convenient terms it would be either -1 or a plus 1. Let us make a distinction as far as the basic terminology goes. This unknown function f, which is a mapping from X to Y, we shall, in the jargon of machine learning, we shall call this function as the target for function. The observations X1, X2, Xn, they're coming from a larger population, capital X. So we can call this capital X as the input space, and the collection of your discrete values, namely -1 and 1, we are designating that by capital Y, and for convenience we call that as the output space. Okay. Now another another thing which we need to freeze before going forward into what the mathematical framework of the machine learning is, that this functional relationship, the true exact relationship, okay, which is mapping your clients to whatever their corresponding approval is, this F. Okay, it is not only not known, but we have to always bear in mind that it is something which is going to be never known. Okay, so once we are saying that this particular piece of information is going to be never known, that means whatever mathematical treatment that we are going to do next, we will never ever attempt even once to find what this exact relationship between X and Y is. Because supposing if, for instance, you knew what the exact functional relationship between your clients and the corresponding credit approval was, then because that rule is known to you in its exact form, So any unseen seen client, whatever the requisite information about him was, gender, loan, and balance, you can always take it, and you can apply your function f and know what his standing is. Okay, that way it is what is happening over here is that you are simply evaluating f. By no means are you addressing the fundamental problem of learning f. Okay, so there is not going to be any machine learning involved if by chance the underlying target small f is known. Okay, so for the theory of machine learning to be absolutely non-trivial, we will assume that this target function small f is not known. Okay, and there is no way that we will ever know what this larger input space capital X is. The whole and sole information that we know about this capital X is whatever n sample data points are, x1, x2, all the way up till xn. Okay, so that is the only part of capital X which is known. Remaining part of this capital X is going to be always assumed as never seen or highly unseen. Okay, okay, and again one further to formulate this framework of learning, we need another missing thing. Okay, so now since these small xi's, they are a random sample which is being picked out of this capital X. So let us assume that there is some unknown probability distribution also on our input space. Okay, so we just introduce this missing block that there is an unknown non-distribution also on X. But we are not going to attempt to find exactly ever what the small f is, what this capital X is, and what what is that unknown probability distribution on that. Okay, these things are there, but these things are not known. Okay, okay, so now we need to manufacture some rule G, again which lives on the same input space X and produces answers in the same output space Y. Okay, we need to manufacture some function G which in some sense comes closest to F. Okay, and how we are going to really make things precise as to in what sense are we using this word closest. Okay. So way the standard machine learning functions is that you are not going to search for G under the sky. You will begin with a certain predefined collection of functions, and all those functions are from X to Y, and from that collection, however, we shall pick out the G which is capturing F the best. So there has to be as your starting point a certain predefined collection. So let us call that predefined collection as the set H. Okay, and we are going to go to give this collection a specific name. It's called as the hypothesis set. So you are going to basically search that given hypothesis set for the best G. Okay, now the thing is let us summarize. Up till now, we don't know what the action of this target F is on this entire space X. We know for sure what the action of the small f is only on those underlying sample points. So we know surely that fxi is equal to yi. But for x's other than xi, we have got absolutely no information as to what fx is. The only thing that we know is that fx belongs to y. It could be either 1 or -1, but we don't know precisely whether it would be -1 or 1. Okay. Secondly, whatever candidate, the best possible candidate that we are searching from the prescribed set H, we know the action of that candidate on this entire space capital X. That means tomorrow if some new client comes and I pull out the requisite information corresponding to him. It means I know what his gender is, I know what his balance is, and I know what his loan is, because the precise formula is available to me for this G. I can easily evaluate G at that point. That is what I mean when I say that the action of G is known fully on X. Okay, but as far as the evaluation of my target function goes, I am constrained to evaluate only on my sample points. And there's no way that I can directly evaluate on that unseen point. Okay. Now let us take small steps and formulate what do we really mean that we are looking for a G that comes closest to F. Okay, let us introduce one symbol. Okay, double bracket, and what the symbol stands for is that double bracket of any expression will be one if that expression evaluates as true, and double bracket of that expression would be 0 if that expression evaluates as false. Now under this symbol, however, we would be able to express things in a more precise way. Let us see. Now your sample is known. So your sample points were x1, x2, all the way up till xn, and corresponding to these known observations, the responses or the labels were also known. So we have fully know fx1, we fully know fx2, so on and so forth up till fxn. Okay. Let us count those sample points on which your manufactured function G does not agree with F. Okay. As I mentioned before, that we have full knowledge of F only on these xi's. because the fxi's are yi's, and yi's are very much present in your data file. Okay, so fxi is known. G was a function which we manufactured by certain ways. So and the G can be applied to even the seen observations and the unseen observations also. So gxi is also known. So it's not hard to see whether gxi is going to be equal to fxi or not. We simply count those points where G does not agree with F. So the proportion of sample points at which G does not agree with F gives you a sort of a measure of discrepancy between G and F. Okay, however, we shall call the proportion of points at which G does not agree with F in the sample. That means on the prescribed data, we call this number as E in of J. Okay, where we are writing it in symbols E in of J, the G, and we are going to pronounce this as the in sample error. Okay, and likewise, we should also see the probability that G does not agree with F on data which is not seen. Okay. Okay, so that means probability of this random variable double bracket gx not fx. We define this expression to be the discrepancy between G and F outside sample. So it's a measure of the out of sample error. Okay, and because this double bracket gx not equal to fx either takes the number 0 or 1, that means it can be regarded as a Bernoulli random variable. And when gx not equal to fx, if you think of that as a success, and gx equal to fx, if you think of that as a failure, rather than there's a very well known fact regarding your Bernoulli random variable, that the probability of the success is going to be exactly equal to the expected addition. So we can also express the out of sample error as the mathematical expectation of gx not fx. Okay, and it is really at this step that we are using the fact that our input space has some unknown distribution. So there is a notion of probability attached to our space capital X. Okay, so we are now manufacturing two different kinds of errors here. The in sample error is your E in. Okay, because your underlying sample is what your underlying data set is, that's going to be always finite. So that's the proportion of this is the number of favorable cases by the total number of cases. So the probability of success in sample. Success means that there's a disagreement or there's an error between the prediction of G and F. Okay, so we have seen that there is we have formulated the concept of E in here, and we have also formulated the concept of E out here. Okay, point that one needs to know is when you look at these expressions very closely. Okay, E in is something which is always known because your Xi's are always known, your G is always known, your F is always known as far as those exercises are there. Number of sample points, capital N is also something which is always known. So E in has a straight forward expression which you can program and you can easily compute it. E out is something which is never known. Okay. Okay. So the whole challenge now is to get a nice looking relationship between E in G and E out of G. Okay. So what can we say about E out by merely looking at E in? That is the challenge. Okay. Look at this expression of E out closely. It is formulated in terms of small f, whose action was assumed to be never known on that entire space capital X, and it is also formulated in terms of the not known probability distribution on capital X. Okay, we want a nice looking relationship between these two. Okay, because the phrase that G learns F, the precise meaning of that phrase is going to come from the relationship between E in and E out. Okay, okay, fine. Okay, now that missing link is filled up by a well-known inequality. So we borrow this result from statistics. Okay, it is the Houghton's law, which connects your E out with E in, and the Houghton's law states this, that the probability that the discrepancy between E out and E in exceeds your predefined tolerance epsilon is always going to be bounded by 2 multiplied by exponential minus n epsilon square. Okay, and then now let's look at this Houghton's law with a little closer eye. Epsilon is something which is provided by you. Okay, if that means how close do I want my E ins to track E out? Okay, so it is entirely my choice whether I keep epsilon as 0.1 or I keep epsilon as half, or I keep epsilon as 0.001. Okay, it just depends on me that how closely I want this E in to track E out. If E in is tracking E out very closely, it means that it can act as a very reasonable replacement for the never known number E out. Okay, so the game here is this. We want to say as much as we can about this never known number E out by looking at the always known number E in. Okay, and the bound on the right is formulated in terms of your sample size capital N. Okay. Now, in case the underlying data set was reasonably large, that would have meant that this bound would be very small. If the bound is very small, then the chance of E in not tracking E out well is also small, because in that case the probability that the discrepancy is exceeding my prescribed threshold is also small. Okay, so that means the probability of it not exceeding my threshold is large. Okay, so that means if we find that the bound on the right is really small, it would then translate as saying that this En is acting as a good replacement for the never known number E out. Okay, okay. And further, that means your E out is in a sense in probability approximately equal to E in. Okay, now if you at the same time are able to shrink E in, that means E out is now also becoming very, very small. If E out becomes very, very small, and you just go back and look at what the description of your E out was, it means that the probability that there is a discrepancy between G and F, that probability becomes small. Okay, so that means the probability that there is no discrepancy between G and F, that is more, or that is large. Okay, so if this discrepancy is really small, you would say that G has learned F well. And if this discrepancy happens to be really large, you would say that G has not learned F. Okay, however, we are going to make these things more clear. We are going to make a clear distinction that memorizing F and learning F are two completely different things. Memorizing F means that you are basically making your E in 0. Okay, learning F means that you are making E out 0. Okay, so the whole idea of learning immediately gets captured once you make this Houghton's bound as small as possible. You would want it really small, because you don't want the Houghton's bounds to be anything more than 1. Because even if you did not know anything about machine learning, you always know that probability of any event is always going to lie between 0 and 1. So if the Houghton's bound is more than 1, it means that there's no meaningful relationship happening between E in and E out. But the relationship becomes immediately very meaningful moment you are able to shrink this bound. Okay, now shrinking of this bound is going to bring E in closer to E out, and simultaneously, if you are able to shrink E in, that will now force E out also to be very, very small. So you can now say that G has learned F well. Okay. Okay, and before we move forward, let us look at this underlying Houghton's bound once more. That bound is 2 multiplied by exponential minus 2n epsilon square. Okay, epsilon as I commented is a tolerance which has been frozen from our side. Okay, so it can be any number lying between 0 and 1. The other thing that you need to evaluate this bound is capital N. Okay, so capital N was what your underlying number of data points were. Okay, and you have seen that lesser this bound, better is your learning. So what does that mean in a very backhanded manner? That in the absence of your data, this entire discipline of ML does not exist. Okay, ML becomes possible only when there is data, because the word learning can now be getting very closely related to shrinking of your Houghton's bound, which is explained in terms of the number of data points. Okay, so So that's going to be one fundamental difference between what your the numerical analysis approximation methods are and what your ML is. Okay. There are a number of scenarios as far as numerical analysis go, which you can handle without data. Okay, but this particular formulation of learning tells you that in the absence of data, the discipline of machine learning itself does not exist. Okay, now the thing is as we have commented before, that has the general procedure that we follow in ML is to first of all get hold of some predefined set of functions, and we are searching that predefined function for the candidate which comes closest to F. Okay. Now suppose that your set H, the set of your defined candidates or the underlying hypothesis set H, there are finitely many options inside that. Okay, so let the collection H have only these members G1, G2 all the way up till Gm. We are looking for that Gi out of these M, which are learning F, the best, means corresponding to that this E out is the least. Okay. Now if you look at your Hawking's law again, okay, right now while formulating this Hawking's law, we were not playing with several GIs. We were playing with only one single G. Okay, but now we are not having one G, rather there's a set of G. Okay, so in this finite case, this Hawking's law takes this form. Okay, the form which this Hawking's law takes is almost identical to the previous one, except that now your error bound or the Hawking's bound is now getting scaled by n. Okay, now one thing which immediately falls as a consequence of the generalized Hawking's bound is that if you are playing with a large number of options, okay, then to kill this bound, that means to shrink it as close to 0 as possible, you would need a larger n. Okay, so as your hypothesis set becomes more and more complicated, in order to achieve this learning, you would need to expand your data set. Because as we have mentioned, that learning means that we got to just reduce this bound. Okay, so if my underlying M is say 20 and my sample points are 10, okay, versus if my M is more, then in order to shrink this quantity 2m multiplied by exponential minus 2 and n epsilon square, I would need a much larger n. Okay, so the main fallout is that learning would in that scenario become feasible only when your underlying data set is sufficiently large. Okay, that is one major fallout. Okay, but there is something uh, which we need to see. Okay, okay, okay. Now if we take a closer look, we just examine this Hawking's law with a little thicker lens. We can always rephrase probability of something greater than epsilon in terms of probability of that thing less than or equal to epsilon as follows. Okay, so you can always rewrite your Hawking's inequality this way. Okay, just because the probability of the difference greater than epsilon was less than or equal to something, so equivalently probability of that thing less than or equal to epsilon would now be greater than or equal to this. Okay, so by mistake, yeah, just make this less than or equal to as greater than or equal to 2. Okay, so there's a probability of at least 1 minus 2m multiplied by exponential minus 2n to 2n and epsilon square, that you will have the discrepancy less than or equal to epsilon. Let us rewrite this this in a slightly different form. Okay, for convenience, if you put delta as 2m multiplied by exponential minus 2n and epsilon square, then you have probability that the error is bounded between 0 and epsilon. That probability is at least 1 minus delta. So there is a 1 minus delta chance that E out would be bounded by E in plus this number. Okay, okay. That means if you are looking at modulus E out minus E in less than or equal to epsilon, so you basically have that E out is less than or equal to E in plus epsilon. Okay, and now when you solve for epsilon in terms of delta, that epsilon will then turn out to be the root of 1 by 2n log 2m divided by delta. Okay, so you can rewrite this generalized Hawking's inequality in terms of a finite hypothesis set equivalently as this. That means in machine learning, we have always been bothered about E out. Now we are saying that and delta is something which you can freeze from your end. If you take delta as 0.1, then you are making this statement with a chance of 90%. That means there's a 90% chance that E out would be dominated by E in plus that term. Okay. Okay, okay. Now the main trap, as far as the real world applications of machine learning go, is the is the following. Even if you are fitting the simplest models to your underlying data, that means if I choose to fit a simple linear model to my underlying data set ax plus b, where there's no restriction on the coefficients a and b, there are infinitely many options. So my hypothesis set now is the collection of all linear models of the form ax plus b. But now there are not finitely many options to choose the best candidate from. There are now infinitely many options from which I need to find out what that best candidate is. Okay, the best linear model which learns F. Okay, and now the thing is, that means in that, even in that simplest case, the cardinality of the hypothesis set, namely this capital M, is finite. So if that is a number which blows out, it means that log of 2m by delta is also blowing out. Okay, which means that overall E in plus this root 1 by 2 and log of that thing is also blowing out. That means I end up with a very unreasonable bound for E out, and there's a heavy chance that my E out is going to be very large. So once E out becomes very large, you will simply say that your G has not captured F. That means G has learned nothing about F. Okay, so does it mean that in the simplest of cases, machine learning is not possible? Had the number of options been just finite, then for me to say that G has learned F well, I only need to increase capital N. That means I can ensure if my survey team collects a large enough data, my model explains F well. Okay, but if in the event of the simplest model that the hypothesis set is not a finite set, again, no matter what amount of data my team turns up with, my conclusion shall always be that G has not at all captured F, because there's a high degree of probability that this E out is large. Okay. Okay. So the main trap with this Hawking's law comes here. Okay. That the immediate fallout of this in the most rudimentary algos is that the conclusion is that learning is not possible. Okay, so to really get around this aspect, we would need to capture some other parameter besides n. So that means that the cardinality of your set H, that needs to be replaced by something more useful. Okay, and that useful thing should be such that this extra term, the second term, root of 1 by 2 and log of 2m by delta, should always be finite. Okay, because once that is finite, you can theoretically shrink that by increasing n. Okay, so now we are looking for that useful parameter which will explain our hypothesis set better. Okay, a merely cardinality of your hypothesis set is not capturing the entire glory of that hypothesis set well. Okay. Okay. So because supposing you are faced with two scenarios. Scenario number one, you choose to fit linear polynomials to your data. Hypothesis set now is of the form ax plus b. Scenario number two, you choose to fit quadratic polynomials to your data. Hypothesis set now is ax square plus bx plus c. Take a cardinality of the first hypothesis set is also infinite. Cardinality of the second hypothesis set is also infinite. Okay, so it is not capturing anything unique about the first set and the second set. We want some parameter which not only remains finite, but it distinguishes how one hypothesis set is going to be special in comparison to the other. Okay, so that distinguishing factor amongst the infinite hypothesis sets should also be there. And now the thing is just look at your basic data set where your responsive variables were either -1 or +1. Mentally, just paint all the entries corresponding to -1 as red and all the entries corresponding to +1 as green. Okay, so and that means that your sample data, there are n points, x1, x2, all the way up till xn. Certain points are now painted red and these certain points are painted as green. Okay, further, every single sample point can be painted as either red or green. So total number of color patterns which are possible on this data set of size n is going to be 2 to the power n. Okay, in your ideal scenario, the total possible coloring patterns possible should be 2 to the power n. Okay, now see these color patterns, they are coming as a consequence of applying your function g to those xi's. Okay, so it is going to be entirely on the nature of this g, whether it is capable of generating every single coloring pattern or not. The maximum possible coloring patterns are 2 to the n. Okay, but it is going to be that hypothesis set which is going to throw up those candidates, okay, which when applied to the individual observations xi are going to give you what should be the corresponding color. So whether that H is powerful enough to generate all 2 to the power n patterns or not, that is something which one needs to see. So what one would really do is, given the hypothesis set H, we will work out how many distinct coloring patterns that we can generate using that H on a fixed sample of size n. Okay, there are going to be hypothesis sets which generate all 2 to the power n patterns. There are going to be hypothesis sets which generate number of patterns strictly less than 2 to the power n as well. There are going to be hypothesis sets which would generate only one pattern or even 0. So any number lying between 0 and 2 to the power n is possible, but surely more than 2 to the power n is not possible. Okay, because the only way that you can paint your observations is either red or green. The total number of observations capital N, so total number of maximum possible patterns cannot be more than 2 to the n. Okay, so once we know what the maximum number of coloring patterns that we can generate using H. Okay, this MHN and in fact turns out to be that replacement for capital M which we want. Okay, now we make this idea of about coloring patterns and the maximum patterns, all that a little bit more formal. So if you pick up some hypothesis from H, say small h, belonging to capital H, it's a mapping from X to Y Y, remember, minus over 1 to 1. So H applied to observation number 1 will either paint it red or green. Then observation number 2, either red or green, so on and so forth. The last observation, either red or green. So basically, this collection, the very first collection that we have defined is the collection of all color patterns which can be generated by capital H. Okay. Again, and now in this collection, your sample x1, x2, all the way up till xn is fixed. What is moving is candidates inside capital H. Okay, and now the maximum number of coloring patterns which can be generated by your hypothesis capital H is now obtained by finding out the total number of coloring patterns corresponding to every single sample of size n. Okay, so we are basically looking at that the cardinality of the first set, cardinality of H parenthesis x1 all the way up till xn, and now you find the maximum of this by varying your x1 to xn. So what does not change in both these computations is your sample size. Okay, so that means the maximum number of coloring patterns is now independent of your sample, but it is depending only on your sample size capital N. Okay, so that is what the formal description of MHN is, and because the total number of patterns cannot be more than 2 to the n, so this MHN has to be bounded by 2 to the power n. Okay, this Hufding's inequality in terms of this brand new parameter known as a growth function MHN looks like this. Okay, and now as far as the theory of machine learning goes, we no longer call this theorem as the Hufding's law. It's called as the generalized VC bound. So the generalization of your Hufding's law to your infinite case given by this theorem of the generalized Vapnik-Sher-Vonnegut bound reads this, that there is 1 minus delta chance that E out is going to be dominated by E in plus omega. Let us call this square root term number 2, we designate for convenience as omega. Okay, now what now if you take a little closer look at what this term number 2 is, okay, this term number 2 increases as the quantity mh goes up. Okay, so that means if your hypothesis set is capturing more patterns, that means that the omega corresponding to that hypothesis set is going to be larger. Okay, so that also means that if the amount of coloring patterns that a hypothesis set captures, if we loosely think of that as the complexity of the hypothesis set H, then omega is the extra cost that you bear by choosing more and more complex H. Okay, if you are working with 3 hypothesis sets, say H0, H1, and H2. Okay, MH of H0, so supposing is lesser than MH of H1, and in turn lesser than MH of H2. Okay, that means the penalty term the cost of choosing H0 over H1 is lesser, and cost of choosing H1 over H2 is lesser. Okay, okay. Now the thing is, it also drives home one important point, that more and more complicated models might bring down your E in very steeply, but at the same time, they might increase your penalty also very steeply. So in reality, what it might happen is that even though your most complicated model is performing really well in the sample, but because your omega is also increasing very steeply, so the sum total is also increasing very steeply. That means there's a high degree of chance that E out is going to be very large, which means that your most complicated model is performing really badly out of sample. Okay, this is going to be one of the things aspects which is very common to ML. One of the most important thing is that you will bring down En, but at the same time you will sharply increase E out. Okay, so one needs to also control omega. And lastly, this is what my last slide is. We demonstrated these ideas through a very simple experiment. Okay, we tried to learn a straightforward function sine pi x. Okay, assume that x lies between minus 1 and 1, and we try to learn this function from a very straightforward data set. We simply randomly chose 2 points on the curve. That means your capital N in this context is N. I worked with 2 very straightforward hypothesis sets. So I am choosing the best possible constant which learns f, and I am choosing the best possible line which learns f. Okay, okay. Results were like these. Watch table number 2. The En. Clearly, the constants are going to leave more error of approximation, and lines are going to leave lesser. But look at table number 1. The performance of constants is better than lines. So the startling conclusion is that constants approximate sin x worse than lines, but constants learn sin x better than lines. So that is all. And what we have covered as far as this initial talk goes is the mathematics of machine learning. What we have not covered in this talk is the mathematics behind the various ML algos. So you might request more talks either in point number 1 or in point 2. Thank you. Yes, sir.
The participants can unmute their mic and ask questions if they want to ask any questions or clarifications. we are very few on the meeting now, so please feel free.
Yes, any questions there?
Niteesh, I just wanted to ask, is it possible to, last example that you showed approximating learning
Yes, sir.
function sin pi x, is it possible to show that outcome on the visually also?
Yes, sir, it is possible, yeah.
Yeah, that will be sort of more illuminating comparison of the two, the constant and the linear. How does this approximate, right?
Yes, sir. Surely, sir, I can show you that, yeah. So just a moment. I'll just load my code, and I'll
Yeah.
just tell you, yeah.
Yeah, no problem.
Yeah, so I'll just load this constant one and the code for ax plus b. Yeah, so I'll just double check whether I'm going to say x. Yeah, fine. There's one more.
Yeah, your screen, you're sharing your screen.
Yes, sir. I'm just sharing that. Okay. Okay, sir. So let me just show you the outputs of my program number 1 and program number 2. So just a moment, if I share my screen and I share this R Studio, if you can see that. So is it, sir,
Yeah.
visible?
Yeah, screen is
Visible?
visible. Yeah.
Okay, sir. So let us quickly, yeah, line by line. If I run this code, okay, that is fine. Okay, okay. So as far as our this example goes, we are learning sin pi x. So in a very artificial setup, I am assuming that my target for function is known. Though in ML, with the general data, you don't assume that, but here our target function is sin pi x. We have loaded that sin pi x. Okay, and we just generate some graph on the interval -1 to 1. So I hope this graph is also visible to you.
Yes.
Okay.
Yeah.
Okay, and then we find out some random samples. So basically we are randomly choosing 2 points on this graph. Okay, so the first point is x, and the corresponding label is going to be y equal to fx. So okay, so after we execute all this and I show some intermediate plot. So we are repeating this exercise over for a large amount of steps. Okay, so that means I am working with about 1 lakh randomly chosen points. And so with this linear the thing, I'm working with about 1 lakh lines of best fit. Okay, so after creating the large number of samples, my mean line, so my average line of all these 1 lakh lines is the line which is currently visible in red. Okay, so these E outs will now be computed with respect to this line. Okay, and now whatever I do and I execute it. Now the numbers that you are seeing, you need to see only the number which I've gotten as variance. You have seen this 1.69, and you are seeing one bias 0.221. E out basically is going to be the sum total of this bias and variance. So the E out in case of your lines is 1.9. So that was the scenario. where we are simulating the data and fitting lines there. And similarly, we can work with constants also. So the basic program remains the same. It is only with constants that your graphs now change, because we are looking at the best possible constant. So best possible horizontal line. And you can see that the variance that I am getting is 0.25 and the bias that I'm getting is 0.5. So E out in this case is 0.75. So that means even though E ins in the constant is going to be higher than the E in case of the line. That is obvious, because line of best fit in 2 points always passes through those 2 points. So E in is 0. It does not happen in case of a constant, so that is non-zero. So constants are that way poorly approximating, but because E out is lesser, it tells you that the constants are learning better than lines. So that is the thing. So we have made a clear distinction between what approximation is and what learning is.
Thank you. Anybody from the audience would like to ask some questions or references or hello, Vamsi. I think probably you can tell some elementary books probably, or some reference which
yes, sir. I'll just type it in the chat or
yeah,
what?
You can add in the chat. That is good enough, so everyone will know.
Right, sir. So one of the first references that you can follow for a reasonably rigorous introduction to a reasonable introduction to machine learning is this book. So Elements of Statistical Analysis. That is the book which is published by Springer. So and its author is Hasty and Tibshirani. So that's a good book. So this is published by Springer. And there's a little informal book also by the same authors. The title is a little different. It's popularly known as the ISLR, in Introduction to Statistical Learning.
Oh, great. Anybody has some doubt or clarification to ask? Well, I think it's still probably they have to get used to how mathematics enters into machine learning.
Right, sir.
Shanmugaraj, would you like to? Shanmuga, you wanted to ask something? No, I think. Okay. So, Niteesh, let me thank you for your clear exposition, how mathematically and the problem of machine learning is formulated, and at what stage statistics enter into picture, and how statistics and probability affect the outcomes.
Right, sir.
Yeah. Thank you very much.
Thank you, sir.
And we will hope to rope you in sometime later on also. Thank you.
Yeah, yes, sir.
So,
thanks, sir. My pleasure.
So please take care and do join the next session, which is going to be mainly on statistics. So that is one of the components required for machine learning.
Okay.
So next,
okay, fine, sir. Sure, sir.
There is a by IIT professor. She is going to talk about basic statistics. What?
Okay.
Yeah. So with that, take care and be safe. Thank you.
Thank you, sir. Bye.
Bye. Bye, everybody.
Okay, sir. Bye.